So in the prior session, we went through the whole evolution from old style OCRs across many generations to where we are today. We summarized the state of the art today by saying that our approach has changed. The way we look at the problem has changed. We look at it as a language understanding problem. We treat in a very rough way, as the authors of a Bait paper said it beautifully, they just treat image as another foreign language, which they call English. Yeah? That summarizes a new or modern perspective on looking at this multimodal stuff, especially document understanding, right? Document AI. Now, this paper is again not very, look at the date of this paper, guys. It's October 2023. Right, so it came around that time. Actually, this is the V2 of the paper. This is Pali 3. I am skipping over Pali 1, Pali 2. Right? And I'll explain what this paper is and why is this relevant for our stuff. And you'll see, one of you have been asking something about images in the things, etc. So you'll see some things here. This paper, now I'm going a little bit beyond just document AI. I'm trying to close the chapter on a multimodal understanding or language understanding. Right? So this paper says, and look at this is from DeepMind. This paper presents Pali 3, a smaller, faster, and stronger vision language model. Now, do you see the wordings now? Vision language model, right? In other words, you treat vision as just a language. Yeah. A vision language model that compares favorably to similar models that are 10x larger. So just to give you a sense, Pali's previous versions were much bigger, right? And Flamingo and there were other models which are much bigger. As part of arriving at this strong performance, we compare vision transformer, VIT models pre-trained using classifier objectives to contrastively pre-trained ones. So remember, we did CLIP. Do we remember CLIP? Contrastive loss image pre-training. What was the loss function there? It was the contrastive loss. Now, one of the things that people realize along the way is that SIGLIP, another way of creating, is just a variational, a different loss function. It gives you better results. So today we look at SIGLIP. So that's all there is to it. We find that while slightly underperforming on standard image classification benchmarks, SIGLIP-based Pali shows superior performance across various multimodal benchmarks, especially on localization and visually situated text understanding. What is localization? Is going and putting the bounding box around things, right? Visually situated text understanding, especially text written on something, so on and so forth. So it says that this paper, this approach, it might not see if they are modeled only for classification, then maybe there are other models that may slightly do better, but this is competitive and it does superior on multimodal tasks. We scale the SIGLIP image encoder up to 2 billion parameters, which is important. See, image models are barely 100 million. So this represents a massive scale-up, right? And achieve a new state-of-the-art and multilingual cross-modal retrieval. So now comes two things, not only images and text, but text in other languages, right? Multilingual. We hope that Pali 3, at only 5 billion parameters, rekindles research on fundamental pieces of complex VLMs and could fuel a new generation of scaled up models, which, by the way, did happen. These days, VLMs and all of these things are very, very active areas of research. Now, I will read up to here because it's really well positioned. And you see this emerging tradition in papers nowadays that somewhere in the introduction they will give you the main contributions. You see, there are 4 contributions. So in all the recent papers, you'll see that authors tend to, researchers tend to mention it upfront. But let's read the introduction. The scaling of vision language models to tens and even hundreds of billions of parameters has shown ever increasing performance. Would you have expected that? And why would you have expected that? Neural scaling laws, yeah. So long as you know how to do it. Meanwhile, models at a smaller scale remain critical as they are more practical to train and serve, more environmentally friendly, and support fast research cycles for model design. Smaller models are more practical in what sense? You and I can train it on our hardware, right? As we saw with the date paper. They're more environmentally friendly. What do they mean?
Less power.
Less power consumption. Actually, to train one large language model these days takes as much electricity as a whole city does, right? Or a small city does per month. It's just a massive electricity drain. In fact, I don't know how many of you know, but almost all the hyperscalers have converged on the fact that the only way we can train AI models going forward at the speed that we want to train them at, there's only one power source that will suffice. And what is that? Right? So everybody is going nuclear. They are all going nuclear. Micro nuclear. Yeah. Micro nuclear. Right? So environmentally is that aspect. And support faster research cycles. Why? Smaller models take less data to train, less compute time to train. So the same neural scaling laws. In the spirit of focusing on smaller scale modeling, we present Pali 3, a third generation family of Pali. So obviously I didn't do Pali, but it is not necessary. I'll explain you this. Let's go to the key contribution. Pali achieves new state-of-the-art results on tasks that require, basically it does an extremely good job. There's suffice to say that. What are the key contributions? We compare classification pre-trained VIT models, the original 16 by 16, to contrastively pre-trained SIGLIP models using the Pali framework. We find that contrastively pre-trained models work significantly better for visually situated text understanding tasks and localizations for the tasks that we get. So SIGLIP, and by the way, this is now well established. SIGLIP models are much better. Second, our model achieves state-of-the-art performance on 10 plus diverse vision language benchmarks, while being 10x smaller in size compared to the state-of-the-art. That means there's something great about the approach, isn't it?
Yeah.
Like it is competing way above its class or its weight size. Yeah? It is almost like a featherweight is taking down a heavyweight in boxing.
The size comparison is number of parameters?
Number of parameters, yeah. Yeah, these days, like you measure potatoes in kilograms, you measure models in parameters.
Good comparison.
Right.
70 billion, 30 billion.
Exactly. For understanding visually situated text, the improvement is by a particularly large margin. So it does this very well. Third contribution, despite not pre-training on any video data, our model achieves new state-of-the-art on several video QA benchmarks, indicative of powerful generalization abilities. So see, you know that your model, there's always a suspicion in a model that, see, a model to some extent, when you train it, partly memorizes, partly learns to generalize.
Yeah.
Right? And memorization is the enemy of generalization, basically. Now, how would you know that your model truly has strong generalization capabilities? By zero-shot learning. It is able to do a task it was never trained to do. Isn't it? That's, so for example, you train it on images, but now you give it a video and it does good at it. It's remarkable. Now, having said that, I must throw in the fact that video is nothing but a collection of image frames plus audio. The whole question is, does it understand deep temporal sequencing or not. And I don't think this one does, but I may be wrong. I don't think the generalization, while is remarkable, it is not that of great practical utility, I would imagine. We introduced the 2 billion parameter VITG multilingual SIGLET model trained on Webley dataset, which sets a new state of the art on blah blah blah. So okay, forget the related work, it doesn't matter. This is the architecture. So pay attention to what this architecture does. You give it, what do you see in the image? I'll just blow up the image. You see a photographer in a hammock next to the beach, right? So nice beach is there, the sand is there, there's water, there's this guy nicely relaxing in the hammock, which is what you would have been doing this Saturday if you didn't have the foolishness to register for this bootcamp. Okay, so let's look at that. Contrastive vision encoder using us with a SIGLET loss function. So what will it do? Encoder will produce a what? A latent representation of the image, isn't it?
Yeah.
Where is that latent representation of the image? This is it. Would you agree? It has created an image embedding. In simple terms, image embedding vector it has produced. Likewise, suppose you give it a text. Let us say that the text is a question. Where is the photographer resting? What do? Text needs to be first tokenized. Those tokens need to be looked up in a token ID, then converted into token vectors, word vectors, and so all of that. But at the end of it, what will happen? They will also, the embedding vectors, you can put into this vector, the text vector, right? Now what can you do? What they are saying is, let's pass it through a transformer. So at that time, because this is, if you look at the people who did this is the DeepMind people, they were big believers in their universal language model, UL, which is a full encoder-decoder architecture. Right. They pass it through a 3 billion parameter language model, both encoder and decoder. And then encoder will do what? Take all these tokens and create one more representation, a transformed representation, and then decode it. Now the thing is, you can choose what the decoding should be. For example, you can train it with a loss function where the output is text, which happens to answer the question. Right? So you see that, right? Where is the photographer resting? You should come up with in a hammock under a tree on a tropical beach. So any other answer is not good enough. So you can train it with a decoder loss function. Does that make sense, guys? Right. So you have, it is, if you look at this picture, isn't it a no-brainer? Right, it's a no-brainer. You train this, and when you do train this, you realize that it does very well. It does good results. On most things, it achieves state-of-the-art results. Right? Here we go. Look at the things in red in the last line. So compared to the state-of-the-art, do you notice that it beats the state-of-the-art for like this, right? Now you can give it an OCR pipeline input. In other words, you can give it a OCR-like task, what is written there, and so on and so forth. It can do that for you. A visually situated text understanding, again, it does very well. It will understand the text and pick it up. You'll see it in the examples. Instead of just looking at it, you can see it. But then they have a much bigger model. Before this paper, they came up with a Pali X. Compare these two. It achieves almost the same results as Pali X, which is a ginormous model, right? Almost the same thing, but at much smaller size. It also achieves fairly good excellent video QA results. And so you notice that these days we are very concerned about model fairness, bias, and other potential issues. So it's a good thing to do, to have a section which talks about potential
Biases.
that, and they have done that. Conclusion is obviously obvious. I mean, there's nothing. what do you conclude? It's a great model, right? That's all it is. Imagine a paper that does publishes a research and at the end of it concludes, and clearly it didn't work out. Yeah. Actually, most out of maybe 20 experiments, one succeeds, but people never write about the other 90. So you can see that it does very well for a whole class of, I won't go into it. It's much better. Why are there no appendix? Oh, significantly better. But anyway, this is this paper. But now let's go to the more interesting and a very, very long paper, PaliGemma, which just came out recently. Now, I don't know, did anybody attend my paper reading on PaliGemma? Probably not. So it's good. So then it's not a repetition for you. What PaliGemma does, remember, in the previous paper, they would pass the token to an encoder and decoder, full transformer, UL2, Universal Language Tool. By the time 2024 comes around, they realize that let's throw in the towel. We don't need an encoder, just let's use a decoder. That's all you need. LLM is just give it to an LLM, basically. Right? So once you have encoded the image and you have the text tokens, all of these tokens just simply give it to an LLM and ask it to decode an answer. As simple as that. Right? So that is the gist of this paper. So look at this. What is different? So let me put it in contrast. Look at the Pali paper. I'll just bring up the image. Yeah, look at this image. You see an image going through contrastive vision encoder. You see the question. You see the hidden latents. The latents are being fed into what? A transformer encoder and a transformer decoder. Isn't it? Now, just this image, compare it to the PaliGemma image. And what do you see? Exactly the same picture?
Yeah.
Right. Exactly the same picture, except that you're feeding it directly into a large language model. A tiny little large language model. That's it. No encoder, just a pure decoder. And it turns out that it works well. Gemma, by the way, is baby version of Gemini. Gemini baby is Gemma. Yeah, open source. So that is it, right? That is the only main difference between this. And obviously, they also brought in a projection layer. They had to, because they have to make sure that you do need a projection to do further transformation. They found that if you do further transformation, and of course align it to this token vectors, same dimensionality, because what they have done is, do you notice that they are using a really huge vision model, 400 million parameter one. And so the latents that come out of it has to be aligned. And also adding one more linear projection gives you more trainable weights to train. And they did that. That's the only addition. And the encoder is one. That's all it is. This is a beautiful paper. There's a lot of detail. It weighs in at some 70 or so pages. But you realize that for you now, at the end of the day, to understand it is quite easy. Are you finding it easy? Are you finding that this architecture totally makes sense? Right? It is again the same encoder-decoder architecture. Right? Image encoder, you're taking English and making it into responding in English. One way to put it.
Is it open source?
PaliGemma, yeah. Not only that, you'll do labs now with it. So guys, this is I hope you enjoyed that. Yeah, go ahead.
So when you go back to that image, the diagram. Now, what is the learning here? Where are you learning the contrast to visual encoder?
No, visual encoder is frozen. You just take a pre-trained good visual encoder and stick it in.
So there is it's pretty much, there's no learning, you're just giving the data.
The learning is in this. What happens is that you open this up and you retrain it. The
Or you
weights here.
retrain the transfer.
And this part also, you do that. The linear projection there. Right. The contrastive vision encoder, you just pick it up. It's a GLIP 400 billion parameter model.
And the paper covers what was the training data set and everything.
Yeah. It has all those details. Right. So PaliGemma is a really good paper. One nice thing is, I don't know, it's the little things you like. I like the fonts that DeepMind uses. You can always recognize their papers by the fonts they use. You see that the paper has a very nice font and layout.
Interesting that all the latest research has moved from universities to these three companies.
Oh, yes. I mean, think about it this way. The people who won Nobel Prize in Science were in the academia. This year, most of them are in Google.
Yeah.
Right? DeepMind seems to have gotten, 3 Nobel Prizes. DeepMind got 3 Nobel Prizes.
Chemistry and
Screen folding, right? Yeah.
Yes. Yeah. Protein folding as well as Hoffield and Jeffrey Hinton. Yes. So guys, look at this task. So training examples. I won't go over all of these, but basically these are pretty tough training examples like this. Caption number. Pizza served, blah, boarded, blah, blah, blah. So you train it with these things, it produces good results. There's nothing magical here. The amazing thing is that they say it actually not 73 pages. It is actually a long paper. It has been well trained. PaliGemma is very practical, guys. Go use it. Very good. It's very good. Go use it. That's the best thing that I can say about it. Use it. It's a long paper. You can read the paper, but I won't do that. 58 pages. Sorry, not 73 pages. 58 pages. It's a long page.
So is it on Hugging Face?
Yeah, everything is on Hugging Face. You can go get it. PaliGemma.
Let's say a document contain latex kind of the images, videos, everything PaliGemma will take. Anything on the document.
It does pretty good. It does pretty good. But try it out. But now, guys, I'm going to give you a task. Out of the box, these models are not necessarily perfection, perhaps. So what you can do is you can go and do further fine-tuning of the models. Where did I put the fine-tuning of the models? Oh, I forgot donut. Sorry. OCR-free. How did I forget donut? My apologies. Guys, stay back for 1 minute. I need to cover donuts. We need to end the day with donuts. I should have ordered donuts for you. Let me walk through the donut part. This is an important paper, guys. It's very important. I can't imagine I forgot donuts. Donut. Okay. Donut archive. Let me go get the paper. Find the paper and get it.
Is it OCR-Free Document Understanding Transformer?
Yes. With donuts. No, this is not the paper. Donut archive. It's again OCR-free understanding of paper. And it brings about the donut. Save as donut. Donut is a significant paper, guys, in this landscape. We must do it. OCR-free. But by now I suppose it will feel a little bit repetitive because by now you have the idea of what we are talking about. Donut. Let's see how quickly you guys can grasp this paper. I know you guys prefer black as a background, so I'll bring it. And So OCR-free, let's read the abstract. Understanding document images is a core but challenging task since it requires complex functions such as reading text and a holistic understanding of the document. Right? So for example, if you're reading a receipt, you don't need to just read the text. You have to know what is its meaning in that page. Yeah. Current visual document understanding methods outsource the task of reading text to off-the-shelf OCR. The reading, you say OCR does it, right? Engines and focus on understanding tasks with the OCR output. Although such OCR-based approaches have shown promising, they suffer from high computation cost, blah, blah, blah. Here, I won't read the details, but suffice is to say that it would be nice, the schema of conventional document information extraction pipeline. You take a receipt. See, this is what happens traditionally, right? You take a receipt. What does it do? As you guys notice with parallel OCR, etc. Do you get an output like this? Bounding boxes and text there, etc., etc. Right? And from there, you go to structured information.
We have to build it.
Yeah, you have to build that. What these guys are saying, as you can imagine, forget about it, right? And just do it in a direct step. How would I do it in a direct step? Very easy. Take the receipt and code it as an image, and then give it to a decoder. Now you can either parse, you can ask it to parse it, you can ask visual question answer, whatever as the input to the decoder, and then produce it. So guys, no magic here, right? It's the same thing. Pretty much by now you would have gotten the sense of what you're expecting. Parse, if you just give it train it with the token called parsing, parse as an input. Here's the receipt and you say parse. It should just create the entire thing for you in a structured way. So it is again, once again, do you notice that it's treating it as a language translation task, right? Exactly. There's no magic here. Important thing to notice is that it's an encoder decoder. Encoder, why? Because if you convert from French to English, you need to encode the French and then decode it into English. And then while you're doing it, you might even ask a question, right? In the end, did Napoleon die? And the answer has to be yes, right? Or something like that. So that's all that is happening. Image goes in. So all of it is, see guys, all of these papers, they all have a great place. But what are they all trying to tell you? That the right way to do documents is as a visual language understanding task. Think of it as a translation task, isn't it? A language understanding task. That's all it is. And as you can see, it does an incredibly good job with handwriting, with this, with different languages, with everything. You can ask questions. And see, sometimes it does make a mistake. So let's point this to it. Let's look at this example. On this, do you notice that what is the name of the passenger? How many of you can make out that somewhere in there, in very tiny fonts, there is this heading called name of passenger. And the name of the passenger is written in handwriting. And because it's visual language understanding, see how beautifully it does that. Dr. William J. Darby. Would you agree? Right. And this is what it comes out with. And the state-of-the-art model that doesn't use this kind of thinking gets it wrong. Right. Sometimes it does get a little things wrong. What is the publication number? Answer is 540, but it gets it wrong. It gets 943. So you have to ask, where did it get 943 from? Publication number is, there must be 943 somewhere in the image that it thought is the, so it extracted another number, 943. Where is it? I can't make out. It's a little hard to tell, but maybe it's here. Maybe 943 is, if I have to guess, it is in such small fonts, it might be somewhere here, right? But the remarkable thing is even those low resolution and those little squiggles, the fact that it can understand is remarkable, isn't it? Yeah. So well, this is it, guys. This is your donut. And actually, I had planned to get you donuts when we did the donut paper, but I think I forgot about it. But this is donut. All of it put together, use transformer-based approaches, use visual language understanding. And as the title of the paper, which is good, OCR-Free Document Understanding. You see that?
OCR-Free.
OCR-Free. And they mean the traditional OCR. Yeah. Though, the way the world works is people will tell you, oh, donut is the state-of-the-art OCR method. Because business is used to the word OCR. Right? So, all right, guys. So
one thing is backbone is a transformer. Or backbone of
everything is transformer these days. Transformers are ruling the roost. Absolutely ruling the roost. And no doubt about that.
I should get some kind of an award soon. Attention, yeah. Guys. I'm not sure about Turing, but something.
Yeah. So, guys, I want you to do one thing. Go to this GitHub page, document-AI-transformers. I will paste it on your at this particular moment onto your chat. Go to this, and the next couple of hours, entertain yourself with this fine-tuning exercise and inference. So you see the inference with donut, right?
Yeah.
You can go to the inference with donut. You can see a Jupyter notebook doing it, right? Try it with some example of your own. You can then play around with these models, LayoutLM, etc. I didn't cover LLM, I'll just skip that, or LayoutLM. But then do fine tuning. Go fine tune donut on this data set. Right? So you will know how to improve. Right? How to improve it.
Nice.
Right? How to improve it for your specific tasks. So you can use it. And as you can imagine, see guys, if you can fine tune a machine to understand this receipt, it is about as bad as it can get, right?
Yeah.
And if it can solve this, it can solve all the easy situations.
Where did you click? Which the data set is it?
No, the fine tuning. There's fine tuning with SROIE. So do this Jupyter notebook, guys. Run it, understand it, see what it is trying to tell you. It's very straightforward. It will take you very little time to. Yes, I'll do that. Okay. Let me go back.
What is the sequence? Donut first and then.
Yeah, just play with donut and then fine tune donut. First play with it, and then so the first link is to just do inference with donut, inference, and then training. Actually, this thing should have been mentioned backwards. And if you go down, you will see that there are lots of resources actually. People have written articles and whatnot, document-free understanding with donuts. So you can see, write things like this, and it will come back with answers. You can give it pretty bad receipts and it will work. So there are medium articles and this and that. But guys, today make it a task to become good with a donut. The other thing I would say is that, okay, let me give you another thing. The TR OCR, go play with the code. Here, this sample code with the TR OCR, go play with it. All of these papers that I've covered, they are there in Hugging Faces and the sample code is all there. So play it out, right? Little notebook.